Welcome to the demo presentation of our IoT project, Smart Power Modules platform. Household expenses can be unpredictable, leading people to wonder about things like the best time to use the washing machine, the current energy consumption of the refrigerator, or the amount of energy used in a day. So the idea of this project is to help people manage their home energy consumption in a smarter, easier and faster way by providing remote monitoring and a mobile and web platform. The IoT platform proposed can affect different domains, for example smart home, smart building or smart grid, and therefore different customers, such as home inhabitants, energy aggregators and house construction companies. This is the scheme of our platform. On the top left corner we have the microservices. Some of them are related to reliability and control applications, others to data analysis and statistical functions, and one of them is used by the developers only for sensor simulation. Then there are the Home Assistant adapter and database. The first one is a script that allows the microservices and the catalog to communicate with Home Assistant. The Home Assistant database instead is a part of the Home Assistant software used to store all data. The Home Assistant GUI is the user interface provided by Home Assistant. It provides users with data plots, statistical analysis and the possibility to control the power modules. Below there is the catalog, the core of the system, and at the end we have the device connectors and the message broker, which interconnect the whole system.
Here we have the resource catalog. The resource catalog essentially works as a device registry system. The primary function is to register and maintain a record of all available devices and the resources they expose. It also connects to a database to store and manage this registered data. On the upper panel we can see the terminal and all the requests that are received by the catalog. On the lower part, instead, we can see the database that was previously mentioned. As we can see, it contains many tables, and some of the most important are the appliance type table, related to the specifics of single appliance types, such as the standby power range, the minimum and maximum functioning range, and so on. Then we have a series of tables related to the devices that concerns time scheduling and other settings for the various microservices, and also a list of the registered devices. The device connector communicates through a REST interface with the resource catalog. It sends and receives data from the broker and the devices using an MQTT interface. More in particular, its main objectives are to register ESP32s to the catalog, to communicate with the MQTT broker, and to implement data translation between the format used by the ESP32 devices and the format compatible with Home Assistant. It also translates the command and inputs of the microservices so that it is able to manage modules and to inform the system about state updates. ESP32s are used to read the sensor and actuate switches. They communicate with each other via a mesh network and send data to an MQTT broker. All ESP32 devices communicate with each other using a master-slave method, where the master is the only one that communicates with the broker. For simplicity, the data and devices used to test the microservices are simulated by the data generation service. At first, we can see on the upper terminal some devices being registered in the catalog, and on the lower side the information related to those devices. Then, the upper terminal panel shows the device connector getting new data, while the lower panel depicts the format of the data being generated and transmitted by data generation. Using data generation, we are able to generate data in different situations, from normal cases to cases in which, for example, some appliances are faulty. Our system offers a range of services. The first one is data generation. We already introduced it. This service, primarily beneficial for developers, facilitates the creation of test data. Then there are a set of control services. They are focused on enhancing safety, providing energy efficiency, and enabling remote monitoring. The timeshift service primary goal instead is to schedule the activation and deactivation of specific appliances. And finally, there's a total instant power that, in conjunction with data and cost analysis, is used to generate informative graph, making the users aware regarding their energy consumption. Now let's focus on the control services. There's the faulty appliances and blackout control service that safeguards appliances from abnormal voltage and power fluctuations. The parasitic load control that detects parasitic consumption. The module power consumption service designed to enable precise control over the consumption of a specific module. And finally, there's the maximum power control that enables power consumption control over a house, assuring that it does not exceed the limits supported by the house electricity meter. Here we have a simple flowchart showing the rationale behind the control microservices. Once we have checked their online presence and their last update, we look for abnormal data. If that is the case, we look at a set of previous values too. If the previous values are unusual, the module is then turned off. Now let's focus on the faulty appliances case and on how it is possible to set it up from the Home Assistant application. As we can see in the graph below, it works as described with the flowchart. At first, high power mode has to be turned on, to signal that only one switch of the module will be active. Then, fault control has to be activated too. Now, the appliance type has to be declared and we can choose whether we prefer to receive a notification only or if the system is allowed to turn off the module if some anomalies are detected.
Now let's focus on the max power control case. It works as described in the flow diagram, so the user is warned when the sum of the powers of the connected devices exceeds the house power limit. In this terminal we can see how the device connector forwards the different measurements to Home Assistant. High power values as for the last device in the terminal can trigger the microservice. We can see, for example, that for Casa Casale the power limit is 600 Watt, but in the previous terminal you could already notice higher values. Therefore, the user is notified by receiving a notification and the device with the highest power consumption is turned off. The microservice of time shift handles the behavior of the modules according to the needs of the user. The latter can choose directly on Home Assistant at the time of switching on or off of a module and for how many days repeat the operation. In this case, for example, we choose to turn off the socket 0 of the smart socket DMJYXNJ module from 1446 to 1450. The user receives a notification to confirm the execution of the operations decided by him. Also on the right terminal you can read the message. The microservice of data analysis provides consumption statistics for each device and for each home. It follows the two steps indicated in the graph. The user can see directly on Home Assistant the consumption of the single module or the current and voltage measurements, choosing automatically the range of days and the time slot. In this case, for example, we can see the statistics between October 13th and 14th for the DODC4MD Smart Socket module.
Now, let's take a look at the user interface. In the panoramic panel, we can see the weather, the username, the state of each module, and their last measurements. For practical reasons, the user can modify the names to make them more recognizable. Then, there is a section about the electricity grid, the house position over a map, and also one dedicated to the shopping list. Finally, there is the socket setting panel, where we can select a module and decide which microservices to use. Everything that we have seen here can be also visualized using the Home Assistant mobile application.